This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is manometer for gas pressure measurement. In this example, we have a water manometer in the configuration shown here. We've got a request to find the gas pressure in gauge and as an absolute pressure if the atmospheric pressure is 0.99 times 10 to the 5th Pascal. So here's a container with gas in it. Here's a U-tube manometer. The outside is exposed to atmosphere, and the difference between the two legs of the manometer is 50 millimeters vertical height. The manometer has water in it. The relationships we're given are that the pressure minus P atmosphere is rho GL, and that the gauge pressure is the difference between the pressure of interest and the atmospheric pressure. Now for these two relationships, P minus P atmosphere appears twice, so let's put the other two pieces together. And here's our relationship that we're going to use. P gauge equals rho GL. Rho is the rho of the liquid in the manometer. That's 1,000 kilograms per meters cubed. G is gravity. In the SI system, that's 9.81 meters per second squared. And L is the length here, 50 millimeters. I'm going to convert that to be 0.05 meters. So the units will work better. And let's look at the units before I crunch numbers. I want to convert this kilogram to be a Newton second squared per meter from Newton's second law, and then I've got 1 over meters cubed. So that takes care of the first bit, and then the next one is meters per second squared, and finally I have meters. We can do some cancellations in here. The second squared is going to go out. This meter is going to cancel this meter, and this meter will change this 3 to a 2, and then we can find that the units are going to be just newtons per meter squared. That's the same as a Pascal. All right, so let's compute the gauge pressure. When I can multiply 1,000 times 9.81 times 0.05, I get 490.5 newtons per meter squared. Now before we're done, I need to ask, is this a pressure that's above or below the atmospheric pressure? And the way to answer that question is to look at the levels, the two legs of the manometer. If the legs were equal, the pressures would be equal. The lower leg is the one with the higher pressure. That is to say, the atmosphere is pushing the fluid in the manometer down. So atmosphere is bigger, so this value is below atmosphere. And the way we denote that is we put a minus sign on for the gauge pressure. So this is a minus gauge pressure, sometimes called vacuum, but I'm just going to say the gauge pressure is minus 490.5 newtons per meter squared. For part B, we're asked to find the absolute pressure, and the absolute pressure, rearranging this relationship up here, the absolute pressure is the gauge pressure plus the atmospheric pressure. And now we've got minus 490.5 newtons per meter squared, or I guess those should be pascals. Let's use pascals. Pascals plus 0.99 times 10 to the 5th pascals. That's the given value up above. And when I compute that, I get 98,509 pascals. Now that's okay, but that's 5 digits. That might be a little more precision than we need. Let me write the answer absolute here. Let me write the answer as 4 digits rounding off to be 98,510 pascals. The number of digits you use, the number of digits you use should be taking into account the implied accuracy. Our implied accuracy is 50 millimeters of measurement and 0.99 up there. Let's recap. In this problem, we've got a manometer where one leg's higher than the other, and we use that information to find out if the gauge pressure is minus in this case. We converted kilograms to Newton second squared per meters to find that the units were pascals. And when we computed the absolute pressure, we had to add back the atmosphere. And then finally, if you remember that the implied accuracy can inform how many digits you need in reporting your answer, then all will be well.